Okay, in this lecture we're going to talk a little bit about debugging, and this comes from one of the very original books about programming in C and C++, one of the ones by Kernighan and Pike in this case. So there was several seminal books written about the C language. The first one was by Kernighan and Ritchie, which was the C programming language, and then there's one about Unix that was written by Kernighan and Pike, and then this version called The Practice of Programming, which is written by Kernighan and Pike. And even though these were written probably in the late 60s, early 70s, the practices really haven't changed that much. They're really still relevant today, especially the basic concepts. Now, tools have gotten more complicated, and therefore some techniques have gotten more complicated, but they all kind of are at the same basis. So let's talk a little bit about some debugging strategies. As well as how to use some debuggers and even some other tools that we might use in the future for some of our programs. And of course, the reason is that the debugging is tough, especially as we get into larger and larger programs, as you're starting to discover. Debugging your little hello world was trivial, and debugging something that converted Fahrenheit to Celsius or some other simple program like that isn't very difficult. But as we get more complicated, we need a lot of different kinds of strategies to debug and find problems in code, not just syntax errors, because those are relatively easy, although you may not think so right now because you're struggling with understanding what the compiler is telling you, compared to some other kinds of problems that we may encounter in the future. The syntax errors are pretty easy. So I want to talk about the difference between testing and debugging. When we're testing, the idea or the goal is and the question we should ask ourselves is, what do I need to do to try and break my program? We talked about the sitting on the keyboard or the butt test, but there's certainly other things, and fairly simple and straightforward and hopefully somewhat intuitively obvious, like, well, if my program expects a number between 0 and 5, I should enter a -1 and a 6. In other words, the outliers from what my expected range is, and make sure that it catches those and degrades appropriately, tells the user that those were wrong inputs, give them a chance to try again, or does something other than just crash and burn. So we need to devise a bunch of test cases, if you will, that do this. And this is part of what the graders do when they grade your homework. They have sets of test cases, and they're looking at seeing which ones your program passes and which ones your program fails. Debugging then is, okay, I know there's a problem because I've broken it in some way via one of my test cases or test strategies, so what do I need to do to fix it? Now, when we start thinking about debugging, there's a couple of times, in our process where we're going to debug different kinds of things. So at build time, in other words, when you're compiling and linking, we're going to get error messages. Those are the syntax errors and the warnings. Those are about the only ones that are going to occur during that time. Everything else is going to occur at runtime, and these are some of the things that we can do to help find those kinds of errors. Certainly we can think before we write the code, and that's part of the reason I'm having you do designs for your program. The better the design, the easier we can translate it into code, and therefore the better it's going to be when we're done, and hopefully the fewer bugs that we're going to find, the fewer problems we're going to find in the final product. There are a lot of bugs that are familiar. We've mentioned some of these already. I jokingly kind of refer to the 5 most common programming mistakes, and they're things like the off by 1 error for an array or a loop, the equal instead of the equal in an if test, those kinds of things, and also missing parentheses and those. So those are a bunch of common bugs, and we'll go through some of those here in a little bit. Beyond that, we can divide and conquer. In other words, one of the things, the strategies that we'll talk about is really number 6, display and output, but that also fits in with divide and conquer. In other words, let's nail down and walk through a process to figure out which section of the code the problem's in, not just assume it could be anywhere in any of the 4, 5, 10 files that we have. Let's try and narrow it down so that we can zoom in on it very quickly, and we'll talk about some strategies to do that. Add more internal tests in your code. So the better you instrument your code for detecting possible errors, like checking the return from an fopen to make sure the file opened properly, checking the return from an fread or fwrite to make sure you wrote out or read in everything you thought you were going to. All those kinds of things will help in terms of, that a problem occurred, you can process a message, maybe you can fix it, but at the very least you can let the user of your program know there was a problem and why the program is shutting down, as opposed to ignoring all those kinds of available information, and then your program crashes and burns, and it's not clear what reason, because it didn't die gracefully, if you will. Displaying output, we can do a lot with various kinds of print statements, as well as log files and all that, to be able to tell what happens when a program goes horribly wrong, or even just slightly wrong. We can also use a debugger. We're going to talk a little bit about GDB. It's not the friendliest debugger in the world, but it is one that's always there on any Linux system, at least. So there are certainly better debuggers, like in the Visual Studio environment and in Eclipse, and ones that are a lot prettier to use and a lot easier to use. And I encourage you to try to learn how to use those too. But we're going to start with the basics and the tools that we know that we have everywhere, which is why we do use a lot of the tools that we use in this intro sequence of courses. And then the other, probably hopefully intuitive thing is, if the code was working and now it's not working, what did I just change? There's a good chance that the problem you introduced was in the section of code you just changed. Not always. Sometimes it causes a ripple effect, but in quite a high percentage of cases, it's going to be wherever you last made changes. Okay, one thing that we have to be able to learn how to do, especially for those build time errors, is understand how to read the error messages. And so, for example, here we've got some preprocessor error messages. We've got some other types. So let's look at these. Here we've written a hello file. I've already circled where the errors are, stdio.h, and then a missing close on a comment, if you will. So let's look at these. Okay, so hello.c 1:20, no such file or directory. So that one should be pretty obvious. You look at that and go, oh, I have an extra letter. Unterminated comment is also fairly self-explanatory. So these are ones where it's pretty much telling you what to do. It's also telling you the line number and approximately the character number on that line. So this says it's in the file hello.c, and that's important to recognize when you have more than one file. It's on line 1 around column 20. Now, the column thing can be tricky, and sometimes even the line number can, because it may not recognize the error until later. Like, that'll happen a lot with things like closing curly brackets or missing semicolons. The actual error message that occurs may be on a line or two below it when it realizes, hey, I'm doing something new and there wasn't a closing curly bracket. So it might be off by a line or two, but you're going to be able to tell, hopefully, by the message what the problem is. And then it's saying on line 2, there's an error, syntax error at the end of input. Notice this was line 3, and this is going back to line 2. That's because this started out with a comment, but there was no close here. So it got to here, recognized there was a problem on this line, and then like, oh, by the way, yeah, we never closed this line either because we're getting to a curly bracket after that. So those are some of the kinds of ways that things might appear to be out of order, but it's really telling you some good stuff. Now, those were all from the preprocessors that deals with comments and pound defines and all that kind of stuff and includes. Here's an example of one from the compiler. We misspelled the word return. That's an executable statement. So it says in function main at line 7, return is undeclared. Because it thinks, oh, that must be a function he's trying to create, and it wasn't declared anywhere. And then there's a whole bunch of errors that tag off that. But notice they're on the same line. So most of the time when you see, even though you got 4 errors, they're all on line 7, which means probably once I figure out what it is, like in this case, and I fix it, all of those are going to go away. It's just there was a ripple effect. When I thought this was a function, then it said, oh gosh, there's no parentheses, etc. So it may, based on the assumptions that it makes about what you're trying to do, it may create several errors when in reality there's only one problem, and fixing that one problem will fix all these errors in this particular case. Which brings up another good point, and that is you should always start fixing errors from the top and fix 3 or 4 and then recompile. In other words, don't try to get through the whole list because some of the ones farther down may have been caused by the ones higher up. So you may not be able to fix them. You may end up changing code that was perfectly fine and now doesn't work because you created errors. I know, especially when you get a really long list of errors, it's kind of scroll off the screen. It's tempting to start at the bottom and work your way up. But typically, because of this sort of cascading effect, it's better to start at the top and work down. So sometimes you get errors from the linker. Like in this case, we misspelled printf. The compiler's not going to pick that up because printf is a library function, stdio.h. But the linker is going to, because it's going to say, hey, I never could find this function. You said there was some libraries we're including, and so I assumed that since I didn't see printf in the current file, then it must be in one of the libraries. But then when I got to linking and started looking at the libraries, I couldn't find that one. And so I get this undefined reference to printf. And then we look at that and go, oh, it should have been printf. So they come from different parts of the process depending on what they are. Now, let's go through those. So those were all the ones in that first category of things that happen at build time. Now let's look at the ones that happen at runtime and ways we can avoid them. So, well, the first one is think before writing. And it's kind of like think before speaking and everything else. If we do something inappropriate when we're making changes or even in our initial design, that's going to create problems later. So think before you write. Think about your data structures and what kind of data goes in them and what are the algorithms we're going to use to change the data structures. Sometimes you spend too much time coding. You need to maybe take a little bit of a break, sleep on it, walk away from it, etc. And one of the mantras that I do all the time, and you're going to probably say it 2 or 3 times in this deck too, is start early. That's one of the reasons we're doing this flipped classroom and trying to work on homework during the class time is so that I encourage you to start early. I try to eliminate as many of the initial roadblocks as possible. You're going to probably run into some more. You're going to have some stumbling blocks, but you have the opportunity to come to class then and get past those. Try explaining your code to yourself, to someone else, to a teddy bear, a giant Wookiee, whatever. Sometimes reading things aloud will let us see things that we didn't see before, explaining it to someone else. Or letting another set of eyes look at it in some cases. And that's okay to do on your homework and stuff when we're dealing with issues like syntax errors and stuff. Now the familiar ones, these are some of the ones I missed before, or mentioned before. The missing break in a case statement, so it falls right through into the next case statement. The equal, instead of the equal in an if test. You can't do compound tests like this in C. You have to have the I in there both times, so you have to say I greater than 5, and I less than 10, or something like that. I and J. This is the bitwise and, not the logical and that we would use in an if test. It's the double ampersand. While C equal get char not equal to EOF, this can potentially create a shortcutting problem that we have to be careful of. So enabling warnings will catch some of these, but not all of them. Divide and conquer, that's a strategy I'm sure you've talked about before and maybe in other classes and other contexts. Certainly it's good here too. When you have a bug that you can't find, try and comment out a bunch of the code until you can get the smallest, simplest section of code that still has the bug, and that narrows down where it's occurring. So take away a lot of the extraneous stuff. Many of you are doing that, writing one function at a time related to your menu, so you don't have a bunch of extra stuff going on there. And you can, you don't have to even do it in the same file. Make a copy and start scaling stuff back, even deleting stuff, and keep doing that until you find the part that has the problem. Then you can go back and fix it in the original file. So always a good idea. Eliminating the code so that you can, and then start adding code back in. If you eliminate so much that you get rid of it, then start adding it back in so you can see exactly which line of code or which section of code is causing the problem. It's always a good idea to add more internal tests. There's some other testing tools that we'll talk about later that you can instrument your code with that are part of the C language and the preprocessor and stuff like that. You also have to be sure you're not suffering from some compiler optimizations that we'll talk about later, etc. Probably one of the easiest ways and most sort of traditional ways to look for errors is with print statements. Print out intermediate information that you're not usually providing to the user, but so you can see what's going on. For example, inside a loop, maybe you print out the loop counter at the top of the loop every time so you can make sure that it's not going too far or whatever it may be. So try to do those kinds of things. And here's some things to think about. And another thing is to make sure you do an F flush when you're printing out debug information, because one of the things that might happen is if you're not printing out very much, it may not trigger the buffer to go ahead and write out to the screen. So the error might occur and your information was there that you needed, but you don't see it because it never got flushed out to the screen. So if you do an F flush of std out, that can help with those kinds of things. And here's some other examples. Maybe instead of printing to standard out, you print to standard error, which also by default it goes to the screen, but we can also redirect it to a file in Linux. So, or create your own log file, write the information to a file. That way you're not dependent on being able to see it on the screen, especially if a whole bunch of stuff scrolls by. You can terminate the program and then go look at the file and see what's going on by looking at the log file. A lot of web servers and stuff create log files. You can certainly also use a debugger because sometimes the errors aren't just syntax errors, they aren't simple logical errors, they're maybe more complicated logical errors. So, and sometimes we can also use the debugger to help us with stuff where the code crashes, because you'll see things like segmentation fault, core dumped. Well, a debugger can actually load up that core file that it creates, actually a file called core, C-O-R-E, really large usually, and we can start debugging at the point that the program crashed, so we can see in the debugger exactly where the program crashed. We can also use debuggers with programs that are already running that maybe are exhibiting a logical error. They're not causing it to crash, but we're getting the wrong answers, and we can attach the debugger to it while it's running, and then we can examine variables and stuff like that. So the simplest debugger that's around, not necessarily the easiest to use, but the simplest is the GDB debugger, which is part of the GNU development environment, which is the environment we're using with GCC, GNU, CCC, and all those. It's even integrated with the Emacs editor. So it's available on almost all Linux systems, so that's one we can use. So if we wanted to use it, for example, if we had a program called testintmath.c that was doing some stuff with greatest common denominator and least common multiple, etc. So let's pretend there was an error in GCD function, even though this one's probably correct. So what we would do is we'd start up the debugger, we'd identify where in the code we'd kind of like to stop, and then we set things called breakpoints. And what breakpoints allow you to do is let the program run for a while, and then at a certain point in the code, stop, not actually terminate, but just pause, if you will, so I can go look at what's going on. I can look at the contents of variables, things like that, and then I can figure out what's going on and see what I want to do next. So in order to do that, first of all, we have to do a special kind of build. So here's an example of what that line looks like to do that build. We build with the -G. Now you may not be using GCC 217, that was on a particular machine, but we're using GCC. But the -G option sort of builds in some extra information into the executable, makes a bigger, a little bit slower executable, but that's okay because we're trying to fix problems. We're not trying to be production model. And so we can do that. Then we can use the Emacs editor, which should be available on most Linux systems as well. And then from within the Emacs editor, which gives us some keyboard shortcuts and stuff like that, we can run the executable file. It shows us how to do that with X, which stands for execute. Execute GDB on testintmath. And then we can set breakpoints. And we use that by doing the word break. So break main would mean set a breakpoint at the first executable line of the main function. Break GCD would mean set a breakpoint at the first executable line of the GCD function. So right after the function definition in your code, whatever the first executable line is, maybe it's a variable declaration or maybe it's a variable initialization, whatever it is, we're going to stop at that point. And then we say run, and what will happen is your program will start running. If there's prompting for the user, you'll get prompted for all that kind of stuff, everything that you need to do up to the point of where you've set that breakpoint. Then it's going to stop and give you a prompt, and then you can control what's going on. You'll be able to see the source code as it goes through there, highlighting the line that's going to be executed next, etc. If you get to a breakpoint and there's nothing you want to do, or after you finish doing whatever you want to do, you can type the word continue, and it'll keep running until it gets to the next breakpoint. But if you want, you can also step through the program one line at a time. So step will execute the next line repeatedly. And if it comes to a function call, it'll step into that function call, so you can actually trace the execution of your program one line at a time. Or next, if you come up to a function call and you just want to go ahead and let it run the function, but you want to look at the next line after the function call, then you can do next, and it'll still execute the function, but it'll step over it. If you don't think that function is where the problem is, you don't necessarily want to step through all the lines in it, you can do it next and skip over and stay at the same level you're at. Let's say you're in main. Now I know some of this maybe sound a little confusing as we're discussing it. You're going to be doing a lab coming up with using GDB and debugger. Give you some code that has some errors in it, and you're going to try to find it, and you'll practice with all this kind of stuff. So you'll have some hands-on experience too. So as you start having problems in these larger programs that we're working on, this will be a tool that will help you with that. So I may want to look at the values of some variables. Let's say I have an I and a j and a temp. I can say print I, print j, print temp, and it'll show me what the current value is at the point that I've stopped of that variable. I can also say where am I in the function call stack. If I'm I want to see if I'm 4 or 5 functions deep, or if I'm in a recursive algorithm, how many times have I recursed so far. So these are all tools you can use, and when we do the lab, you'll have some more choices as well. And then when you're done, you type quit. You can exit Emacs, and then you're back to whatever command prompt you were at before. Now I can do other stuff too. You can actually provide command line arguments to a function. You can redirect standard in and standard out. You can break conditionally. You can put if tests on the break, like break only if I is greater than 10. So if you want to break on a loop, but you want the loop to run a bunch of times, and only if I gets greater than 10 you want to stop, you can do that. And there's several good utilities, several good tutorials out online for GDB, etc. We also talked about focusing on recent changes. This is sort of a fairly intuitively obvious way to look for possible problems. If I just change something, the chances are, and then suddenly the code isn't working, that's probably where the problem is. And that brings us to making sure you don't do lots and lots and lots of changes and tests and then go test and try to debug. So it's easier if you write a little, test a little, debug a little, write a little, test a little, debug a little, because you've got smaller segments of code where the possible problem could be. And also keep previous versions of your code. Rename before you go make a bunch of major changes to a particular code file. Make a copy of it, name it save 1, save 2, save 3 as an extension or something like that. One of the nice things about Linux is you can have as many extensions as you want, and they can be as long as you want, whereas in Windows it's only one extension. It has to be 3 characters, like .exe, okay, or whatever, or well, 3 characters or less, because you can do .c. So that way, if you are doing major changes, like in your homework 2, where you're making major changes to homework 1, save those older versions, because you might go so far and realize you really screwed up and you want to go back, and you're not going to be able to remember all the things you have to undo to get back to that version that you had before. There are also tools to help us do that. One of them is called RCS, but there's various kinds of revision control or version control tools to help us do that. We're not going to use this one in this class, so I'm not going to go through this in a lot of detail. I guarantee if you take any of the game programming sequence, you'll use one called Subversion. And in the project management class, for those of you who end up taking that, either as an IT major or just as an elective, very good class. You'll learn about using Subversion and stuff. Excuse me. And there's some other ones out there like CVS. RCS is a very simple, personal one. It works well for one developer. It's part of most Linux distributions, etc. Other ones are better for multi-developer projects where several people are going to be interacting with the same code. So they control who can edit the file, so only one person can edit the file at a time. You can do rollbacks, like say roll back to the previous version. So like for example, when you get Microsoft updates and it says it's version 8.2.3, that means it's under some kind of revision control, and they can roll back to 8.2.2 if they want to, or even all the way back to 7.0.0 if they want to, because all those are versions that are maintained by some kind of version control system, so I can get back to the older versions if I want to. And there's a few slides here on how to use RCS. We're not going to go through that in detail. It's certainly here if you'd like to use it. I'd certainly encourage you to try it if you want to. It will help you in maintaining versions of your code and perhaps recovering things that you might otherwise have lost. I know a couple of people have come off and said, I had all this code and I lost it. Well, at least with the version control, you can go back to a previous version and have most of what you had, if not everything. So it can also merge versions and do all kinds of other things that we're not going to talk about. Okay, so basically remember this table as we look at this, and there's a couple added footnotes here about using a debugger and using RCS. But build time is when we're looking at just error messages from the compiler, the linker, or the preprocessor. All the rest of these things have to do with strategies, either to avoid creating bugs to begin with, or for finding bugs once we've realized that there's something wrong in our code. Of course, memory management can be one of the hardest things to debug, dealing with pointers and dynamic memory allocation. So these are some things to watch for. For example, in this example, we've created an integer pointer, and then we're assigning some value to it, star p equals, but we've never declared memory for that. Remember, the pointer isn't memory for where to store the integer, it's just pointing to an integer. So we call that the dangling pointer as one example of it. Here's another one. We've created a value, we created a pointer, but again, we haven't assigned it any memory, and yet now we're trying to read a string into it. So that's another example. All these are examples of that. Here's another one. We create a pointer. In this case, we actually allocated space for it. Then somewhere later on, we freed it, and then we tried to use it again. So again, it's still a dangling pointer because the pointer does not have legitimate space associated with it. Other kinds of similar type or common bugs, memory leak type bugs, where, like in this example, we declared a pointer, we allocated space to it. We come along later and allocate space to it again, but we never freed this old space. So now there's this old space out here that's an orphan because there's no pointer pointing to it. There are tools that will help us check for that too that we can use. Here's an example of creating space, freeing it, and then freeing it again. This is going to create a runtime problem because we're trying to free memory associated with a pointer that we've already freed. So somebody else might have that now. We're actually freeing memory associated with another program or even another part of our program, neither of which is going to create nice things to happen. Some other ones. Allocating not enough space. So let's say you're allocating for a string. If you look at this particular string, HELLO, that looks like 5 characters, but remember there's a null on the end, so it's really 6. So when I allocate space for S2 to fit that, I'm saying malloc string length of S1. Now remember, string length doesn't count the null, so it's going to say there's 5 characters. It's going to allocate space for 5. Then when we do the string copy, we're going to copy 6. But that 6th one, the null, is not going into space that belongs to S2, so it may get overwritten or something else. So we also want to be careful doing the same thing instead of saying string length, doing size of. Okay, so we're not allocating enough space in that case. And then also other things where we might allocate not enough bytes. Here we're saying the size of a double pointer when we really meant the size of a double, which is what we need to allocate to that. Because a double pointer on a 32-bit machine is always going to be 32 bits, whereas the double is 64, the actual value, etc. So those are things we have to watch out for. Other things about memory management, if you get a segmentation fault, it's probably one of those things above, but you can also use GDB to open up that core file and find out what line it's at. You can put asserts in your code. Asserts are kind of a form of an if test, but you don't have to comment them out later when you don't want to use them anymore. You call assert to make sure something's not null. So you say assert, and in parentheses you say, P not equal to null, and you're asserting that's true. As long as it's true, nothing will happen. If it's false, you'll get a message when your program fails. In addition to the segmentation fault, it'll say something like assertion P not equal to 0 failed. So at least you know where to go look in your code because you know where you put that assert function call. And of course you can do manual stuff too and instrument code with your mallocs and callocs and all this kind of stuff. Also make sure you don't hard code the number of bytes. Use size of and stuff like that so you don't end up with a problem on different architectures. You can also comment out freeze and see if errors disappear. You might be freeing too soon, or you might be freeing memory that's already been freed, so sometimes that will help you find those kinds of errors. There's also a tool called meminfo. You can build programs with GCC flags that will let you get additional memory information at runtime. So, and there's other tools out there too for specific platforms. Like there's some memory leak tools for Windows, and some of them are free, but some of them cost money too. But if you're in a commercial environment, they're going to want you to use those tools because they can't afford to have problems with the code when it gets out to the clients who are paying big money for it. All right, that brings us to the end then of this section on debugging. Hopefully some of these strategies will help you as you start working on your next couple of homework assignments. As always, feel free to bring questions about this deck of slides to class, the next class period, and ask particular questions about problems you're having with debugging your own code. We'll see you in class.